Good afternoon. Can everybody hear me and see the slide?
Yes.
Okay.
Yes.
Thank you. Are there any questions?
Yes, I got a question.
Yep.
So, is there any chance that we could go over the test so that we could learn, so that we could do better on the next one?
Go over what?
I mean, we can go over a test so that we could do better on either the next exam or the final.
Well, if you ask specific questions, I will answer them. I am not going to go over the test
Oh,
wholesale.
I'm sorry about that.
If you have a specific question, I'll be happy to answer it.
Okay, sorry about asking that.
No, it's just I'm not going to just talk about it if you're not interested. If you are interested, you should be able to ask a specific question.
Okay, got it.
I have a quick question about the
Yes.
test. For the first question, would you mind just kind of roughly going over the process to derive the language from the grammar? I think I had trouble doing it. I think at the end I was able to get it, but I just kind of want to know if I had the general process right.
You want to get the language of the first question. So you're going to get, hold on, I have to deal with that. We have S goes to B, B, or C, and A goes to B, or C, and B goes to S, B, and C goes to A. Well, I mean, you basically, the easiest way is to first look at, I would look at the C. All right, so that means we have A goes to B or A. So that makes the C disappear in this case. All right, and from that we can obviously get that A gives us a bunch of A's, 0 or more, followed by a B, followed by the same number of A's, I greater or equal to 0. So that is what we get from the A. So that takes care of that. And then we have S goes to little b, capital B, and capital B goes to SB, so that gives us this. So that gives us S goes to VSB, and or C. And of course, C gives us, if we look at that, that gives us A, I, B, A, because C has A, and A is this, and so we have A, little a, capital A, little a, so that's one more little a, and so we have S goes to BSB, or this. And from that we can get that we have B to the S generates, I'm sorry, this should be a star, B to the J, followed by I, B, A, B to the J, where I is greater or equal to 0, and J is greater or equal to 1. Or if you want to consolidated, then you have here one or more A's, same number of A's here, one or more B's, same number of B's here. Does that answer the question?
Yes, that helps a lot. Thank
All
you.
right. Any other questions?
Yes, I had a question.
Sure.
What's the best way of contacting you outside of class? Because I tried to email you a couple of times and haven't heard anything back over the couple of weeks.
Well, I will remember there are many, many students in this class. There are about 250, so I haven't quite gotten to everybody yet. If you've sent me email, I will respond.
Okay.
Okay. Sorry about that, but there are about 240 some students in this class. Any other questions?
Could you go over number 5, the Greibach normal form?
All right. S goes to A, or little A goes to BS, B goes to SS or B. All right, so that is the question, correct? And oops, all right, there. So the first one is fine. S goes to AA. There is nothing to be done. A goes to BS. There is nothing to be done. B, so there we have an S, which means we have to replace that S by capital A, followed by the S, or little a followed by the S. And then, of course, we have B goes to A. So, of course, I'm assuming the order is S, A, B. And so we have B goes to, well, there's the A, so we have to replace that by BC, AS. And then we have AS, so we got that. And now we have to do immediate left recursion elimination, so that gives me BAS or ASB prime. And B prime is CAS, CAS B prime, AS or AS B prime. So that is now, we have S, we have A, and we have B and B prime. So this is where we are. And now we have to do the substitution back in. So we have B goes to AS and ASB prime. That,
Professor, I think the C should have been an S.
I'm sorry, you are absolutely right. That should be an S. Thanks. S. All right. Okay. So now we have to do we got the B, which is okay. It starts with a terminal and has nothing else. Then we have to do the BAP substitution. We have to plug the B into the A. So this is A goes to AS. That's where the error comes from. ASS. So we plug in that B goes to AS in here for that B. And we have ASB prime S. So this is what we get by plugging the stuff for B into production for A, so this is fine. And now we can do the S. We can take the S, which is A, S, S, followed by capital A, S, B prime, S, A, and then little a. So that is now the process. That's now what we have for the S. So S, A, and B are okay. And now we have to plug in B prime. We do that last. So we have these three S productions. So we have A, S, S, A, S. So we plug that in here. And A, S, B prime, S, A, S, and A, S. So we plugged in those three right-hand sides for that S. And then we plug it in for this S. So this is A, S, S, A, followed by A, S, B prime. And then we have A, S, B prime, S, A, followed by A, S, B prime. And then we have little a, followed by A, S, B prime. And of course the other two, A, S and A, S, B prime. And so now we have the B prime, which means we have this, we have that, and we have that. This is now, that would be the final answer of Greiburg normal form, the stuff that I circled in blue. Okay?
So you were able to finish this in about, I would say about 4 minutes.
I don't hear you. You have to speak up.
Let me see. So, Professor, you were able to finish in minutes, right?
I was what?
The test took 2 hours, but I was not able to finish the test. Is this like I was not able to actually, I did attempt all of the questions, but I didn't do them all completely. Will we get credit for some of it?
You will get partial credit, but you obviously won't get full credit if you didn't finish.
All right, thank you.
Okay. Any other questions?
Yeah, what happened to the big B to little b production?
Big B to little b. Oh, well, yes, I forgot about that one.
It went sort of bad, but judging by how everybody else did, oh God, I thought it.
Any other questions? All right. Now, we have a number of things to do today. And the first one that I want to do is look at closure properties. Closure properties, if you remember, we were looking at regular languages. And so we had two regular languages, and we looked at the union. We looked at the concatenation. We looked at the star. We looked at the intersection, and we looked at the complement. And in the case of regular languages, REG, they're closed under union, concatenation, star, complement, and intersection. So let's try to do the same thing if we have context-free languages. So CFL. And so we have two languages, L1 and L2, that are context-free languages. And we are interested in finding out whether the union of these two arbitrary context-free languages is a context-free language or not. We're interested in whether the concatenation of two context-free languages is, again, a context-free language. Whether the star of a context-free language is a context-free language. Whether the intersection of two context-free languages is, again, always a context-free language. And finally, the complementation of a context-free language, is that always a context-free language? And so, in order to answer that question, let's assume we have two grammars, GI, in I, T, we can assume they're over the same alphabet, PI and SI, where I is 1 and 2, and N1 intersection N2 is empty, so they don't have anything in common. No variables in common. Obviously, the terminals are the same, but that doesn't really, I mean, if you have two different terminal alphabets, you just form the union of them and then use that for the T, so that is not really a problem. What is important is that, of course, we want to make sure that they don't have anything in common. In particular, the starting symbols are different. So, in order to see whether the union of two context-free languages is context-free, well, it would be good if we could construct a grammar that would simply generate all the words that are generated by G1, as well as all the words that are generated by G2. And that is not particularly complicated, because what we can do is we can generate a union language, a grammar, which is N1 union N2 plus a new symbol, starting symbol. T, of course, is the same. P1 union P2 union S goes to S1 or S2, and then the starting symbol of that new grammar is S. So basically, the key issue here is that we have two productions. S goes to S1, first grammar, or S goes to S2, second grammar. And so once we are in S1, we can do everything that we can do in G1. Once we are in S2, then we can do everything we can do in G2, and so that obviously allows us to do exactly the union. So the answer is that the union of two context-free languages is always guaranteed to be a context-free language again. So let's try the concatenation. Well, obviously, this is not particularly difficult to see. We're going to do exactly the same thing, N1 union N2 union a new starting symbol, and we have the same terminals, and then we have the productions of the first grammar, productions of the second grammar, plus a single new production, S goes to S1, S2, and then S is the starting symbol. So that means the key issue again is that production S goes to S1, S2, which means that we go to S1, S2 in the first derivation step, and then from S1 we can get everything in L1, and from S2 we can get everything in L2, which means that this is again a context-free language. Always guaranteed. So CFL are closed under union concatenation. So now we want to do the star. So there is L1 star, and so we have G star, which is N1 union a new starting symbol S. T, of course, is the same terminals. P1, we have all the productions that we had in the first grammar G1. Union, and now we're going to generate basically the star, which is S goes to S1, S, or epsilon. And S then is the starting symbol. So that these two productions allow us to generate any number of S1s. 0, which would be S goes to epsilon, or 1 or more. So we have S goes to S1, S. So the S then lets us loop as many times as we want. Eventually we will terminate with S goes to epsilon, and so we then have as many S1s as we want. So if we want to generate L to the M, then we can generate S1 to the M by using M times S goes to S1, S, and then one more production, S goes to epsilon, to get rid of the S, because obviously eventually we'll have to get rid of that starting symbol. And then we have M copies of S1, which will allow us to get M copies of L1. So that means that the star is again a context-free language, and that shows that context-free languages are closed under under star. So now we want to check whether the same thing holds for intersection. And well, what would you guess?
They don't.
They don't. Why do you guess that?
Because you can't prove what's not in there because you're not actually looking at that.
I don't follow. I mean, we could show it for regular languages. The intersection of two regular languages is a regular language, so regular languages are closed under intersection. Why wouldn't that be true for context-free languages? Well, all right. It turns out, well, I'm not going to preempt that. Let's look at two grammars. So we have S goes to A, S, no, hold it. S goes to, S1 goes to AB, and A goes to A, B, or AB, and B goes to C, B, or C. So what does S1 generate? Well, it obviously generates the concatenation of what we get from A and what we get from B. In A gives us a bunch of A's, little a's, followed by the same number of B's. So it follows then that this grammar generates A to the I, B to the I greater or equal to 1, because we have to have at least one A and one B. And then from capital B, we get a bunch of C's, one or more, because B goes to C. There is at least one. So that is what we get.
Professor,
Okay.
could you explain one more time? This is probably a question that would have to do with the Greibeck form. I also had
No,
this.
it has nothing to do with that.
Well, no, whenever you were actually setting up the actual information. Sorry for number one, not the Greibeck form. But what I wanted to see was A leads to the same number of A's and the same number of B's, right?
Yes.
That's you mentioned that. What it
Well,
says
that follows from that.
or
Capital A generates little a, capital A, little b, so you can keep on replacing the capital A by AB, or you can replace it by AB, in which case you got rid of the capital A.
And then that gives you the same amount of A's and B's as well?
Correct.
Okay.
And then the C, the B, capital B, generates a bunch of C's without any further restriction. So C to the J of them, there's at least one. So this is the language that this grammar generates. Okay? And now I'm going to look at another grammar. S2 goes to CD, and C well, let's make it easier. Yeah, let's leave it that. C goes to little a, C, or A. And D goes to little b, D, little c, or B, C. So you can see that this is very similar to that first grammar, except of course now the capital C generates a bunch of A's, one or more. Is greater or equal to 1. And then the D, capital D, generates B, a bunch of B's, little b's, followed by exactly the same number of C's. So this is B to the T, C to the T, T greater or equal to 1. This is really just the same thing that we had here for capital A. That's now the D, except it generates B's and C's rather than A's and B's for the capital A. So this is now the language that the second grammar generates. Okay, everybody clear about that? So basically, the capital C just generates a bunch of A's, which really has very little to do with everything else. And the D then basically generates bracketed B's, little b's and C's that were matching. If you want to consider B as an opening parenthesis and little c's are closing parentheses, then you basically have nested parentheses. So that's what that second grammar generates. And now let's look at what happens if we take the intersection. So this is our grammar G1, this is our grammar G2. So let's take L1, L of G1, intersection L of G2. What is that? Well, it's any word in that intersection has to be in this language, but it also has to be in that language. So if it is in the first language, then the number of A's has to be equal to the number of B's. If it is in the second language, then the number of B's has to be equal to the number of C's. And any word that is in the intersection has to be in both of them. So that means we're looking at A to the L, B to the L, C to the L. L greater or equal to 1. Correct? And what do we know about this language? What do we know
It's
about
not regular.
Pardon?
It's not regular.
Well, it is not regular because neither of these two are regular, but that's not the question.
Could I ask, it looks like they would be the same, but basically if I and S were different, they wouldn't, and if I, J, and TT were different, they wouldn't. Is that right?
Well, okay, you look at the first grammar. The first grammar requires you to have a bunch of A's followed by the same number of B's, followed by some number of C's. Right?
Oh, I see. Yeah, they don't have to be the same. I get it.
In the second grammar, you have a bunch of A's followed by some other bunch of B's, followed by exactly the same number of C's. Okay? Now, if a word is in both this language and that language, then it has to have a number of A's that is equal to the number of B's, because it is in the first language, and it also has to have a number of B's that is equal to the number of C's, because it is in the second language, which means that the number of A's is equal to the number of B's, and that is equal to the number of C's, which is A to the L, B to the L, C to the L, for L greater or equal to 1. And what do we know about this language?
That they're all the same number.
Yes.
L would be the same, and so that means there's a contradiction because...
No, there's no contradiction.
I'm sorry. Well, it just seems it's...
There is no contradiction. What did we do a week ago? I know I blew it when somebody asked me, will this be on the test? And I said, no. Yes. It's not context-free. This is not context-free. If you remember, we showed that this language, using the pumping lemma, we showed a week ago that this language is not context-free. And that means we have now demonstrated that the context-free languages are not closed under intersection.
I'm sorry, could you explain again why this is not context-free?
Yes, please.
That's something we showed a week ago. Using the pumping lemma, correct. If you remember, it was A to the N, B to the N, C to the N, but it doesn't make any difference whether we call that index L or N or anything else. The issue was that we had a bunch of A's followed by the same number of B's followed by the same number of C's. And that we showed a week ago, that this language is not context-free by obtaining, well, we applied the pumping lemma. We assumed that it was context-free. That means there was...
Wait, I thought that was showing that it wasn't regular. I thought we had applied the pumping lemma to show that it wasn't a regular language, not that it wasn't...
Two pumping lemmas. The first pumping lemma was for regular languages. The second pumping lemma was for context-free languages. The second pumping lemma said if we have a word that is Z that is long enough, and we quantified exactly what long enough meant, but that's not really that important, then there exists U, V, W, X, and Y such that Z is the concatenation of these five. And we know that V and X can't be both epsilon, so the length of V and X is at least 1. And we can then say that V to the I, W, X to the I, Y is also a word generated by that grammar. And of course, using this pumping lemma, we then showed that this language was not context-free by obtaining a contradiction in each of the cases where we assume what V and X is all about. So if you remember, we had, I don't remember, something like 14 different cases that we distinguished, and in each case we got a contradiction, and that meant that in every case there couldn't be this decomposition, Z is U concatenated with V concatenated with W concatenated with X concatenated with Y, such that Vx are not both epsilon, and V to the I, W, X to the I, Y is again a language. Z long enough is that there is the constant in the pumping lemma, which is basically 2 to the capital N minus 1. Where N is the number of variables in the grammar in Chomsky normal form. That we did all that a week ago. And so if Z is greater in length, strictly greater or equal to 2 to the N minus 1 plus 1, then that makes it long enough. And in that case, you have this property, and that allows us to show that this language is not context-free. And because this language is not context-free, and it clearly is the intersection of these two context-free languages, it follows that context-free languages are not closed under intersection.
Professor, could you go over what it means in this situation that is not context-free? I know it's a step back, but it's actually last time we were doing regular expressions, regular languages.
No, we were not. We were doing context-free languages. We were doing this pumping lemma, and I showed exactly that this is not a context-free language. What does that mean? There cannot exist a context-free grammar that generates it.
Yes, but I think last time we actually did it on, like, if I remember correctly, we did the same exact example, but we did it in terms of whether it was a regular language or not whether it was
That may
context-free.
be what
Yeah,
you
that's what I
did,
remember
but
too.
I didn't. I did not do that. I did it exactly with context-free languages.
Do you
Okay,
recall which day it was?
Pardon?
Do you recall which day it was so we can review the?
A week ago, Monday last week.
All right, thank you.
I'm sorry. When the exam was, I'm sorry, Wednesday last week.
yeah, it seems, I think a lot of us do not remember that part. Is it possible that we can, like, kind of go over that just a little bit?
That would be great.
Look, I mean, I completely covered that last time, a week ago, and I can just dig out the slides and show them to you because I don't really have time to go over everything twice. If there are specific questions that you have, I'm willing to look at them, but I don't really have time to repeat everything again. So let's see, where are we? So there it is. So let me see whether I can share this particular screen. This is what we, oops, come on. Do you see the screen now? G is Chomsky normal form. Can everybody see the screen?
Yes, I can see it.
It has green stuff and red stuff and blue stuff. Right?
Awesome, thank you.
Okay, so that is where we started. By assuming that G is in Chomsky normal form, we obviously were talking about context-free grammars, not anything else. Okay?
Okay, thank you.
So, and that was the pumping lemma. If Z is a word in that language and Z is long enough, N is the number of variables of the Chomsky normal form grammar, then there exists U, V, W, X, Y in T star terminals, such that Z is the concatenation of those five things. And if we repeat the second and the fourth in tandem S times, then we get again a word in that language for all S. And we know that V and X cannot both be epsilon. That is the pumping lemma for context-free languages. This was the slide that I the slides that I produced last time.
Excuse me, Professor. So for a word that's greater than the length of Z, what do we plug in for S? Would it be like some S equal to 0, which would contradict the length of Z?
The issue here is that this has to hold for all S. Okay? And because it has to hold for all S, you can pick a specific value for S. All right? And it still has to be true. And if it is not true, then obviously you have a contradiction. So if you look at the example, at the proof, we looked at the claim was a week ago that A to the N, B to the N, C to the N is not context free. I'm repeating basically the slides from then. And so the claim is that does not exist a context-free grammar, and we assume that there is one, so there exists a context-free grammar. You can assume without any loss of generality that this grammar is in Chomsky normal form, and n, capital N, is the number of variables in that Chomsky normal form grammar. So then we take Z to be A to the N, B to the A to the 2 to the N, B to the 2 to the N, C to the 2 to the N, which obviously is long enough, okay? If you go back to the pumping lemma, that obviously is true. This is 3 times that number, more than 3 times. Okay, so it is long enough. And then you'd simply have to enumerate all possibilities. V could be epsilon, in which case X can't be epsilon. It has to be A's or A's and B's, or only B's, B's and C's, or only C's. And then in each case, we can pick a particular value for S. Remember, it has to be true for every S. Therefore, if I pick a specific S, it has to be true for that. And in each case, we get a result that the word that we obtain by taking that particular value for S is not in the language, even though it is, of course, generated by that grammar. And so we have this, and we have V only in A's. We get V is only A's. We get the same 1, 2, 3, 4, 5 different possibilities. If V contains A's and B's, then we don't really have to mess with the X, because just taking S is equal to 2 is going to give us immediately a contradiction. Same thing if V contains B's and C's, S is equal to 2. And if V consists only of B's or only of C's, then we can simply set things S to 0, and that means we have not enough B's and not enough C's. So in every single case, we have, in every single case of those 14 cases, we have a contradiction, and that then proves that there cannot be a context-free grammar that generates that language, which means the language is not context-free. So that was what we did a week ago. And so let me go back to the slide that I produced today. So everybody sees this now?
Yes.
Says intersection. So we have now shown that because this language is not context-free, there cannot be a context-free grammar that generates this language, that the little class of all context-free languages is not closed under intersection. Because if it were closed, then the intersection of any context-free languages would have to be context-free, and we have now shown that that is not true for these 2 specific languages. So context-free languages are not closed under intersection. So we've seen that context-free languages are closed under union, they are closed under concatenation, they are closed under star, but they're not closed under intersection. And then the last question is, what about complementation? And that is, of course, fairly trivial. Are context-free languages closed under complement? You should be able to answer that already.
No,
No, why not?
I think you have to use intersection to solve that, right?
Right. So if you have intersection, then intersection of two languages, L1 and L2, is of course L1 complement union L2 complement, the whole thing complemented. So if context-free languages were closed under complementation, then we would now have in this formula a proof that they would be closed under intersection. Because if they're closed under complementation, then L1 complement would be a context-free language. L2 complement would be a context-free language. We've already seen that the union of two context-free languages is a context-free language. And then that means that union is a context-free language. And then the complementation of that would again be a context-free language. And that would then prove that the intersection is a context-free language. And we know that that isn't true. This is not a context-free language. We've seen that context-free languages are not closed under intersection. Therefore, context-free languages are not closed under complementation. So, whereas in the case of regular languages, intersection and complement work. So if you start with a regular language and you complement it, you get another regular language. This is, of course, flipping in the DFA, final and rejecting states. That does not work for context-free languages. Not every context-free, not the complement of a context-free language is not necessarily a context-free language. Okay? So you can see that there are fairly significant differences, certainly as far as closure properties are concerned, between regular languages, which are closed under practically everything that you can throw at them, and context-free languages, which are not that closed, certainly not closed under intersection and not closed under complementation. So one of the methods that we use to deal with regular languages were finite automata. We used other things, regular expressions, regular grammars, certain systems of equations, but probably the one you can relate to most immediately is finite automata. You basically feed a letter at a time into that automaton, and you keep transitioning from one state to the next one, consuming in each transition a letter, and so that means that eventually you end up in a state, and if that state is an accepting state, then you can conclude that the word that you started with in the initial state and consumed step by step is going to be accepted, which is in the language. If this is a deterministic finite automaton, then of course you have a unique path, and that means if it is leading you to a rejecting state, that fact that the state is rejecting means that the word is not in the language. That's of course not true if you have a non-deterministic finite automata, because there may be several paths from the initial state to some states using the same word, and some of them may end up in a rejecting state, And some of them may end up in an accepting state, and if that's the case, then of course the fact that there's at least one accepting state that can be reached immediately indicates that the word is accepted. But if you have a deterministic finite automaton, you have, of course, a unique path. And so if that path ends in a final state, then you obviously know it is accepted. But if it ends in a rejecting state in a deterministic finite automaton, then you can conclude that the word is rejected, because that's the only path that exists for that word in the deterministic finite automaton. So the analog for context-free languages is a push-down automaton. The difference, if you think about what was it that we could not handle, what, if we go back to when we showed that there were context-free languages that weren't regular, we did, for instance, A to the N, B to the N. We showed that that language is not regular, but it is obviously context-free. And so what is it that made that not regular? Well, it was the problem is that we have a bunch of A's, and then we want to determine that it has exactly the same number of B's. That ability to compare the number of A's and the number of B's is what made that language not regular. So the inability of being able to look at basically count the number of A's and compare it to the number of B's, that inability for regular languages makes this language not regular. It's, of course, something that can be done using a context-free language, because obviously, well, we've looked at this. This is a context-free grammar, and therefore, it generates precisely that language. And so that means that we have clearly a mechanism, a context-free grammar, that allows us to generate this language, the words in that language. So how do we capture this ability of counting? Well, in the finite automaton, there is no counting ability. You can count modulo something, but you can't count. So in the example that we did, where we looked at the number of A's, we counted modulo 4, and we ignored the number of, no, it was the number of B's, I think, something like that. And so in that case, the finite automaton can count modulo something, but it cannot count. And that, of course, shouldn't be too surprising, because if you think about this N is unlimited. And so if you were to be given a bunch of A's, huge number of A's, then you would have to be able to record how many A's you've seen. And that, of course, then implies that you have to have an unlimited amount of storage. Because if you have only a certain fixed number of bits to store, then that, if you have say, B bits, then you can't store anything larger than 2 to the B. So if I give you something that has 2 to the B plus 1 A's, then you're screwed. Because you can't really record that there were that many A's. And so that immediately shows that this whole idea of a finite automaton is not going to do you any good in dealing with this counting issue, because you basically need an unlimited amount of storage. So how does a push-down automaton handle that? Well, a push-down automaton is basically a finite automaton plus a stack, where you can record how many A's you've seen by simply putting a marker on that stack for every A you've seen. So that stack is obviously unlimited, and so you can push n A's onto the stack, and when you see the first little b, you take the last A off the stack, meaning you now match that last A with the first B, and you remove that A from the stack. And then you keep on going until you, well, until when? Until the stack is empty. If the stack is empty at some point, then you know you've seen exactly as many A's as you have seen B's. And if that's the language you're interested in, then at that point, the push-down automaton should accept.
So
what that means, pardon?
If you have more B's than A's, won't you get to an empty stack, but then continue to try to pop from the stack?
Right, and so you fail, and so that means you crash. So if you don't stop in a regular way, and we'll formalize that more carefully, but basically if your stack is empty and you're trying to remove more stuff from the stack, well, if you try to do that in a program, your program crashes. And the same thing is here. But we're sort of finessing that by having a bottom marker, and in that case, if you try to go beyond the bottom marker, then that is immediately an indication that this word is not accepted. So in this particular case, if you have 3 A's and you have 4 B's, so the 3 A's will remove the first 3 B's will remove the 3 A's, and then the 4th B attempts to remove another A. That A does not exist, so that at that point you end in failure, and that means that that word is not accepted. I mean, ultimately, it is an automaton, and as all automata, it says yea or nay. Is the word accepted or is the word not accepted? And if the word is accepted, then the automaton will explicitly say, yes, it is accepted, and if the word is not accepted, it can reject it in various ways, for instance, by trying to do something that is illegal, such as removing a marker from the stack that isn't on the stack. Okay? So what we then have is we have an input, which typically is 1 at a time. And we have a finite automaton that does the reading of that input. And it has a read-write head for the stack. And that means our push-down automaton then will consist of 7 things rather than the 5 we have for a finite automaton. We have an alphabet of input symbols. We have a set of states. Now the stack, of course, is its own universe, and as such it has its own alphabet. Gamma. We have a move function. We have an initial state. We have an initial stack symbol, and we have a set of final states. So if we look at the first, second, fourth, fifth, and last component, then by and large, and the by and large means I have to do some restricting for the move function, but by and large, this is what the red stuff that I underline is essentially a finite automaton. The gamma is the stack alphabet of stack symbols, and the Z0 is the bottom marker of the stack. So there would be your Z0. So T is the alphabet of input symbols. Q is the finite set of states. Gamma is the alphabet of stack symbols. Delta is the move function. We'll look at that in more detail. Q0 is an element of Q. It is the initial state. Z0 is an element of the stack symbols. It's the initial stack symbol. And finally, F is a subset of the set of states. It's the set of final states. So if you look at the red stuff, basically that is, for all practical purposes, a finite automaton. But we now threw in that stack with its stack symbol and its initial stack symbol. So we have to look at the delta. Delta is basically, well, let me write it down. It maps a state and a stack symbol and an input symbol. Now, we're going to be with push-down automata. We are willing to accept a single letter from the input alphabet, but we're also willing to entertain epsilon, meaning that we're not consuming any input symbol. And we map that into subsets of Q cross gamma star. That looks like a handful. It's not really as complicated as it is. So we have delta of a state Q and a stack symbol and an input symbol. So this is a state, this is a stack symbol, and this is either a terminal or epsilon. So if this is epsilon, well, then that means we're not consuming anything. And so this then basically says we are having stuff that consists of a state and a string over the stack symbols. So because this is the subset of all the set of all subsets of this, it means that effectively we have a state, a pair consisting of a state and a string of stack symbols that is an element of this delta QZA. So let's look at a simple example. Let's do A to the n, B to the n. So that means we are in a state Q0. We have to start somewhere. We have a bunch of stack symbols. We have the initial stack symbol Z, and we have a marker. We basically write down a marker for every A that we're going to see. And so we start this whole process, and we have an A, we could see a B, and we could have an epsilon. So initially we are in Q0, we have the bottom marker, the Z, on the stack. So there is our stack, there is our Z. And now if we see an A, having Z on top of the stack, we're going to go to state Q0, and we're going to put on top of that Z an X. Now, the way this is interpreted, so if we have QZA, that means we're consuming little a, we see the Z on top of the stack, and we're in state Q. And if we have P gamma, element of this, then that means we're now moving over to state P, from state Q to state P. We consume that A, and we replace the Z by gamma. So effectively, in order to be able to put that X on top of the Z, we have to replace the Z, and we replace it by XZ. That essentially is what we're doing. And that will become clearer in a minute, because when we want to remove a Z, then basically the gamma is epsilon. That kills the Z. So at this point, we've consumed a single A, because n is greater or equal to 1, so we have to have at least one A. And then if we have more A's, we stay in Q0. We put another X on top of that X. So now we have a bunch of X's, one for each A that was consumed. And so if then we see a B, in that case we have to go to another state, because at this point we then want to switch context. We want to say now in Q1 we are going to kill off X's. So we obviously don't ever want to see an A. We only want to see B's. And so because we already removed, we saw that X and saw a B, so that X then is removed, and that's why we can't have a B initially, because that would not be appropriate. And so if we then have more X's, then we stay in Q1 and remove the X's. And obviously, we don't ever want to see the Z when we have a B. So how do we end? Well, we go to state QF, which is a final state. And in that case, we don't do anything. And we can make sure that nothing is going to happen by removing the Z, and that then guarantees that the stack is empty. So obviously, if one had some stuff for QF, that would not be applicable because the stack is empty. This requires a stack symbol, so if there's nothing on the stack, then obviously at this point everything stops. And so that is then the push-down automaton for that language. A to the n, B to the n, we basically see an A, and we record the fact that we've seen an A by putting an X on the stack, and that depends on whether we start, which is when we have Z on top of the stack, or we have an X, which means we have already seen an A, and now we see another A, and we keep on putting X's on top of the stack for every A that we see, and then at some point we probably will see a B. And if that is the case, then we are removing that X and change to another state, Q1, and in that state Q1, we simply remove X's for every B that we see. We obviously don't want to see any A's because that's no good. And the whole process then ends by seeing a Z on top of the stack. And in that case, we make an epsilon move. We consume epsilon. Obviously, the assumption is that there'll be nothing there. And then we go to that final state and to the epsilon. So what does it mean we accept? Well, we can accept by final state. Which we have here. So in that case, if we end up in that final state QF, and of course the assumption is always that we consume the entire input. Clearly, if there were more B's sitting there when we go on to the final state, that would not be acceptable. This is the same deal as in a finite automaton. If we get to a final state, but we haven't consumed all the input yet, that doesn't do us any good. That word is not accepted unless we've consumed the entire word. So the fact that we go to that final state will only result in the acceptance of that word if that is the entire word. If there's stuff left that should still be processed, then obviously that word is not accepted. So this is acceptance by final state, so we end up in a final state. However, push-down automata also have another way of accepting, acceptance by empty stack. What does that mean? Well, it means that a push-down automaton clears out its stack. Now, once it's cleared out its stack, obviously nothing will happen. You can't move because the move function requires you to have a stack symbol. If there's nothing on the stack, then that Z does not exist, and that means you basically crash out. So that means you can then, instead of saying I will accept a word by final state, if it gets me to that final state, it can be, a word can be accepted if it gets me to an empty stack. Again, of course, the entire word has to be consumed. And if that ends up clearing out the stack, then that will also be a way of accepting. And if you look at this example that I've given you for a to the n, b to the n, this actually clears out the stack as well. It does not just get you to the final state, qf. It also clears out the stack, because the only way in which you can get to that final state, qf, is by taking this move, having z on top of the stack, being in state q1, consuming epsilon, and then you replace the z by epsilon, which means the stack is empty. And so at this point, the automaton will have an empty stack, and therefore, even if you were to say that you don't want to accept this language by final state, you basically say, no, I don't have a final state, it would then be accepted by empty stack, because the stack is empty. So there are two ways of accepting, and if we have a push-down automaton, then acceptance by final state is denoted by L of P, and acceptance by empty stack is going to be denoted N of P. So these are two different languages that can be associated with a push-down automaton. In this particular case, both modes of accepting will end up with that language, a to the n, b to the n. And so that means that in this case, it would not make any difference whether you want to accept by final state or by empty stack. Obviously, if you didn't have qf and epsilon here, if you had qf and z, meaning that you're not replacing that z, then that would be only acceptance by final state and not acceptance by empty stack, because the stack would not be empty if you were to replace that epsilon here by z, in which case stack is not empty, but you would go to the final state. So basically, we will have to define at next time on Monday what we actually mean by accepting, and more specifically what we mean by moving. So we start with a configuration. We have an initial state q0, and then we have the entire word, and then we have the initial stack symbol, and we have moves, and if that gets us to some state P, consumes the entire word, and has a gamma on, that's the stack, stuff on the stack, then acceptance by empty stack is gamma, well, let's go in the order. Final state, if P is an F, then this is acceptance by final state. If gamma is epsilon, then it's by empty stack. So these are the two possibilities. Final state, P is a final state. Empty stack, gamma is epsilon. In the case of acceptance by final state, it is immaterial what the gamma looks like. In the case of acceptance by empty stack, it is immaterial what the P is. And I am running out of time, but basically, if I have a state Q and WA and Z gamma, this is basically a configuration, and I will make one move. This is 0 or more moves. Now, one move, it going to get me to P, W, and alpha gamma. If that delta of Q, A, and Z contains P and alpha. So basically what that means is if we have this situation, so we have, for instance, let's say we have two A's and two B's. So this is your Q0 and Z0, Z. Okay, so this is the initial configuration. And then we have one move, so that gets us to Q0, because we have Q0 and XZ with the A. This is the A that we have here. So this is, we consume one A, so that leaves us with A, B, B. And we have on the stack now XZ. So this is the first move, and then the second move would be we're in Q0 again, because we have now X and A, so we consume that second A, so that leaves us with two B's. We have X, X, Z. Then we have the next move. Well, now we have a B. We're in state Q0, that gets us to state Q1. And we have one B left, and we have XZ, because we removed that X. This X was removed because it is replaced by epsilon, so that basically is removing it. And then we have another step, which is Q1 and epsilon and Z. I'm running out of space, so let me read. Yeah, let me go up here. So I have here Q1, because the Q1, you seeing an X on top of the stack, this is this situation, Q1 and epsilon, so I'm replacing this epsilon, this X by epsilon, so that gives me Q1, and I have now consumed that B, which means I'm left with epsilon, and I have a Z, because I replaced the X by epsilon. And now I have the last step, which is QF. And I obviously consumed epsilon, which means I'm not consuming anything. And I replace the Z that I see with epsilon, so I have this. And that means now I have both a final state, QF, and an empty stack, epsilon. Any questions? All right, then we will continue next time. What we will show is that whether we accept by final state or by empty stack does not change the power of that particular mechanism. So any language that can be accepted by empty stack can be accepted by final state, and any language that can be accepted by final state can be accepted by empty stack. So the two modes of acceptance are in fact equivalent. And then we'll take it from there. We will then have to show two things: that whenever we have a context-free grammar, we can construct a push-down automaton for the language accepted by the generated by that grammar. So the push-down automaton accepts exactly the language that is generated by the context-free grammar. And then conversely, to show the equivalence, we have to show that for any push-down automaton that accepts a particular language, we can generate a context-free grammar that generates the same language. So that then establishes that context-free grammars and push-down automata are equivalent. And with that,
Could we go, Professor, before you finish, could we go over each one of the slides so that we
Sure, no problem. Okay, let me see, where am I here? All right, slide 1. Slide 2. And there's obviously a B missing.
So you would essentially have 10 productions.
Yes, yes. That has consequences. And then we have slide 3. Then we have slide 4. Slide 5. And slide 6.
Can we go back to 1? I need to take one more picture of that one. Got it. Thank you.
All right, anything else? I will talk to you then on Monday.
Thank you.
Bye-bye. Have a good evening.